Hi everyone, my name is Dmitry Vasilevsky. I decided to record this video in response to one of the comments on my previous post, which was about the use delta connected CTs in transformer protections. The comment suggested that a delta CT connection only filters out the zero sequence currents, while the transformer overcurrent protection, for example NC51, may still operate undesirably due to positive and negative sequence currents. Today let's discuss this topic and see how the symmetrical component currents are actually distributed in a power system. Let's start from the simplest possible circuit, consisting of a voltage source, a transmission line, and a single line to ground fault or SLG fault at the end of the line. As you know, for the SLG fault, the positive, negative, and zero sequence current are equal at the fault location. For example, if we close these switches to apply SLG fault at the end of the line, this vector diagram will show us that the positive, negative, and zero sequence current are indeed identical. This is what the theory of symmetrical component describes. However, there is only true at the fault location. What happens to the sequence current in the other branches of the network? To understand this, let's move to a more realistic example, a 210 kilovolts network. Here the distribution of the sequence currents becomes more complicated. The grounded neutrals of the power transformers provide additional return paths for the zero sequence currents. However, there is no path for positive and negative sequence currents. Let's place two digital meters along the transmission line. As you can see, the related vector diagrams appeared on the right hand side of these simulation models. Now this is a steady state operation condition. I will hide the voltage vectors for clarity. And I'll disconnect the transformer load by switching all this circuit breaker. The transformer is now operating under no load condition. These are just steady state magnetizing current. And finally, let's switch from phase current to the symmetrical component currents. Now the vector diagrams show us that only the positive sequence current is present. The next step, let's apply the SLG fault between these two digital meters. We will be applying a single phase A to ground faults, so we should pick up this item, A0. And now you can see the actual distribution of sequence currents in this system. Between the source and the fault location, all three sequence currents are present. However, beyond this point, beyond the fault location, only the zero sequence current is present. As I mentioned before, this happens because there is no path for positive and negative sequence currents. Look at these digital meters with number 3. It represents a current transformers supplying the transformer over current protection. Since only the zero sequence current flows through the CTs, a delta CT connection will completely block entire fault current from reaching the protection relays. Let's demonstrate this. Let's switch to the secondary quantities. For these digital meters or measurement element 3, the upper vector diagram shows us primary currents, which are the same as in previous window, and the lower vector diagram shows us the secondary currents, which depend on the CT connection scheme. Only the phase currents are displayed here, but it's sufficient for our demonstration. With the CTs connected in star and a transformation ratio of 30, the secondary current under SLG fault condition are approximately 23.6 amperes, which is well above the CT rated secondary current. In other words, this secondary current could cause an undesired operation of overcurrent protection of the transformer. Now let's switch the CT connection scheme in delta. As you can see, the secondary currents has practically disappeared. Only a few milliamperes remain. This is exactly the point I made in my previous post. A delta CT connection under SLG fault condition completely eliminates the external ground fault current from the HV side over current protection. That's why a delta connected CTs or their virtual equivalent implemented in modern IEDs are used to prevent an undesired operation of the transformer over current protection. If you are interested in such experiments, you can find the free simulation models on our website, which is located at pro-rpa.com. There are some models for different experiments. If you enjoyed this video, please subscribe to the channel where you are watching it. We are going to publish many more videos on relay protection. Thank you for watching and see you next time. Goodbye.